ahead and pick a multi-substituted benzene. So in each of these cases, so you guys remember, did we already look at bromonitrobenzene and the toluene to ethyl toluene? Did both of those, right? Okay. So let's try para-nitrobenzoic acid. Yep, this will be an interesting one. Okay, so what we're going to try and do is synthesize this compound from benzene. Okay, let's stick with black. So we can draw in a happy little benzene. Yes, I said happy. And we want to know how we can make our product. So in this case, I wrote it out as the full long name. I don't expect you to do nomenclature for the exam.
At all?
For aromatic nomenclature, sorry. So we can go through and address the individual pieces on this. Nitro, and then we have the ic acid. So the nitro means we've got the NO2, and the ic acid means we have a carboxylic acid. Okay, I put them on in the correct positions, but how do we know where those correct positions are? Because of the P out front. Okay, P stands for para, which means our two groups are on opposite sides of that ring. Okay? So to address this problem, we have to come up with a way to get these individual pieces onto the ring. Okay? So let's take a look at what our electrophiles could be. So of those two substituents, have we seen a functional group that would allow us to put on one of those electrophiles? So this is where you'd have to go back to the 6 primary, so I hold up 3 fingers, the 6 primary electrophiles that we've looked at before in the previous slides. I actually haven't shown you how to put that one on. That one's actually tricky.
The C elements of the triple bond with oxygen.
I haven't shown you how to do that one either.
Yeah, we did that.
Oh, no, that's, yeah, we'll talk about that too in a second. The nitro is the primary one that we've talked about on how to put on there. Okay? To get that on there, what we're doing is breaking that off, and we're putting on NO2 as our electrophile. Okay? How do we get NO2? Where does that come from? What's that? We have to add H2SO4 and HNO3. Okay? So to get a nitro onto a benzene ring, those are the reagents that I need to add the nitro to get that put on there. Yes?
If this was on the test, could I put HNO3 first? Or?
The order won't matter in this case. Okay? The only time the order matters if we put a number out in front. We say 1, 2, which we'll have to do with this problem at a later step. Okay? So if I add nitric acid, so if we go back to our benzene, so this is going to involve a lot of probably crossing out for you guys. Okay, just so you're aware, I'm trying to walk you through how you should approach it, which is going to lead us down a lot of wrong paths. So we could go through and say to the benzene ring, let's add, and here I'll go ahead and swap it on you, HNO3, H2SO4. That reagent generates our NO2 electrophile, which can then react with the aromatic ring in an EAS type reaction, and I make my benzene ring with the NO2 attached. Yes? No?
Yes.
Good. Okay. As far as how do you know that, you have to know that H2SO4 and HNO3 generate the nitronium ion, which can then react and act as a substituent. Okay, you have to know that. There's no way around it. Okay, that's something that you would need to have memorized or on your cheat sheet. For those of you that weren't here Tuesday, you're allowed an 8.5 by 11 cheat sheet, front and back. Write whatever you want on it. I don't care. Okay, probably something helpful about organic chemistry, preferably.
Could you put it anywhere?
You can put it. So why do we pick that carbon to put it? Well, it's doing a substitution reaction with a hydrogen ion. So one of the other products here that we aren't drawing is H+. Okay? So a hydrogen came off of our benzene ring, and in the process of it coming off, the nitro replaced it. Okay? So we go back to our benzene, and we can look at 6 possible locations where we've got hydrogens. Are any of those locations different from any of the others? No. So does it matter which hydrogen I take off, where I put the nitro? No. So that's why I can put that nitro wherever I want. Okay? Does that make sense? So for the next step of this reaction, okay, we would then have to be able to add some reagent, some extra thing here, okay, which I'm just going to say is step 2, and that would be our other piece. Okay, before we even getting into figuring out how to put that other piece on, let's think about where that piece would go on the ring. Because now if we go through and evaluate the hydrogens on our aromatic ring, they're not all the same. Which means this nitro is now going to have an effect on which of those hydrogens is allowed to be substituted in the next step. Okay? So regardless of what species I react with at this point, my electrophile is going to go to very particular locations dependent on that nitro. Does that make sense? Okay. One of the things that you would have to know about the nitro group is something about its Lewis structure. So we can go through and draw that, and we get something along these lines. Too many lone pairs. Wow, that didn't help. Get a negative charge here and a positive charge on the nitrogen. This is a multi-substituent effect, so what we now have to do is evaluate our aromatic ring, and in particular atom X, like we did with our previous substituent effects. Atom X in this case is what atom? The nitrogen. It's the atom immediately bound to the ring. What can you tell me about that nitrogen? It's positively charged. When we looked at our atom X effects, we ranked our atom X based on does it have more electrons or less electrons than hydrogen, than a hydrogen atom. How many electrons does a hydrogen atom have? 1. How do we get less than 1 atom or 1 electron? It has to be a positive charge. So let's go through and take a look at our atom X, nitrogen. What's its charge? Positive. Does it have less electrons or more electrons than a hydrogen atom? By definition, it has to have less. That is why it is positive. If atom X has less electrons than hydrogen, what effects do we have with our ring? It's a deactivating effect, which means our reaction would react slower. Did the question ask anything about how fast the reaction went? No, so that's irrelevant. Okay, what else is the other feature? It directs to the meta position, okay, which would be the 3,5 positions. So if I'm going to take this species on and react it with whatever my electrophile is in step 2, I would expect that electrophile to go to the 3 or 5 positions. Okay? According to what I want to make, where do I want that electrophile to go? Para. Does adding the nitro first work? No. Okay? Which means all that work we went through and did, that step, while it may be valid, nitric acid and sulfuric acid to add the nitro group, cannot happen first. Okay? Like I said, this is going to involve lots of erasing. Thankfully for me, it's really easy.
What?
Okay? The nitro directs to the meta position. What's our product? Our product is para. If we add the next electrophile, it's going to the wrong position for our product. We cannot do that step first. Okay, so and that was a bad idea for me to erase it all. Dang it. What's that? Yeah. Now I got to draw it all back on. Yeah, it's rough. Okay, so we said the nitro does work, so we know the reagent for the nitro, so we might as well hold on to that information, because that is helpful information. to add the nitro, it's going to happen in a later step, so it can't be step 1. So at this point, we'll mark it as step 2. To add the nitro, I need HNO3 and H2SO4. This next part gets kind of tricky. So that means we have to then be able to add this substituent first. Okay, our carboxylic acid substituent first. If we go back to those 6, again with the 3 fingers, the 6 electrophiles that you need to know for the EAS reaction. Which of those 6 adds a carboxylic acid functional group? One of them adds a carbonyl, which is what you were referring to earlier, the acylium ion, but that's not a carboxylic acid. Should be pretty hard to find. We didn't do it. Okay? So we've got to think a little bit further ahead, okay, or further back to how we got a carboxylic acid on an aromatic ring, because we have seen that. When we first talked about the aromatic ring reactivity, what is today? Thursday? Last Tuesday. We did talk about putting a carboxylic acid on the benzene ring. How did we do that?
Magic.
Chromic acid. Chromic acid reacting with what? So to get our chromic acid, or to get our acid on the ring, our carboxylic acid on the ring, what did we have to do? We had to react with chromic acid. Okay, what did we react with chromic acid? Actually, I'm going to write it as chromic acid.
I just wrote chromic acid, chromic acid.
Well, where'd the benzene ring come from?
It had the CRRH attached.
Yeah, that's why.
Where'd the benzene ring come from?
Oh, it was a benzyl.
There we go. No, you're absolutely right. Benzyl, meaning we had the aromatic ring, we had a carbon off of it, that carbon had to have a hydrogen. As long as I have that hydrogen, chromic acid will react, removing all the carbons, leaving me with the carboxylic acid. Great. Okay, that's helpful because now I know how to get the acid on the ring. Okay? However, what's the further problem? Do I have this on the ring yet? Do I have my isopropyl on the ring yet? Darn it. So what do we have to do? Now we have to figure out how to add the isopropyl to the ring. Red's a bad choice. That's not why it's a bad choice. How do we get the isopropyl on the ring? Sorry. What atoms have we added to the ring here? What are these? All carbons. What's another way that we could refer to carbons generically? R group. A methyl is too specific. We can get an R group. Can we possibly, of our 6 possible electrophiles, did we ever add an R+? Did we ever have an alkyl cation add to our ring? From those 6 important electrophiles that you need to know.
Where are those 6?
Those 6 are in your, so if you've got the textbook, let me pause that real quickly. Sorry, I stopped recording. If I take benzene and I react it with isopropyl chloride in the presence of aluminum chloride, trichloride, I can add my isopropyl group. Okay. Once I have that isopropyl group, I can now react that species with chromic acid to make my acid attached to the ring, my benzoic acid. You guys follow the steps? Okay. And unfortunately, these are all things that we've already talked about. Unfortunately, you're required to have all that information either written down on your note sheet or have it memorized. Okay? So you've got to be constantly referring back. If you're trying to do any of the homework or any of the quizzes straight from memory, guaranteeing you right now you are doing it wrong. Okay? There's no other way to tell you than you are doing it wrong. You must be referring back to your notes. Okay? Yes?
Where does the, right there, above the, yes, nope, right there. How does that, how do you get that?
Where do we get it from?
Is it just reacting together and that's how you get the group?
Yes.
So it's not like.
That's the R plus. R stands for
Whatever.
carbons,
Random.
period. Any carbons we want.
Right.
What's this? Carbon
Right.
attached to other carbons.
Oh, so
This
then,
group right here is our R plus.
What makes it a plus?
so you have to know
When
that
that
it's
C
got the
comes
additional
off.
carbons because you know that it has the three.
Because of what we decided we wanted on here.
Because of the first one.
Because of the first
Because
one.
of the other one.
Not because of the other one was a secondary feature. So we went through and said we needed an aromatic, we needed the carboxylic
Right.
acid on
That's
it.
what I'm talking about, because of
So we
that.
go back to our chemicals and we say, we have seen getting a carboxylic acid on a ring. How did we do it? We had to add chromic acid. To what? Chromic acid had to be added to a benzene ring that had a benzylic hydrogen.
Because it oxidizes it all the way down.
Because it oxidizes
That's
it
why
all the
double
way down.
bond goes to oxygen.
Exactly right.
And that carbon turns to oxygen.
And we get rid of those carbons. You're not responsible for knowing where they go.
They just float away.
Yep.
Magic.
I told you.
Ah!
Okay? What you're responsible for is knowing that when you add chromic acid to an aromatic structure that has a carbon immediately attached to the ring with a hydrogen on it, it turns into a carboxylic acid. You're responsible for that reagent, that reaction. Just like in this next, or the previous step before that, to get that R group, that carbon-containing group, to attach to the ring, I'm going to have to attach it to an alkyl halide to make that carbon positive. Why does the carbon need to be positive? So, no oxygen. So it attaches to the ring. Remember, your ring is a source of electrons. For it to react with this and form a bond between our ring and that atom, what charge does that atom need to be? Positive. So it has to be attached to an alkyl halide, or a halide. That makes that carbon partially positive. It's not positive enough to react, so what do we add? A Lewis acid catalyst to make it more positive.
So then that chlorine goes.
So then that chlorine is kicked off, making this carbon formally positive. It now reacts extremely quickly with our benzene ring, and we get our intermediate alkyl benzene. Once we have the alkyl benzene, we know that reacts with chromic acid to get the benzoic acid that we needed in our final answer.
This is going to be on the test, isn't it?
I don't know. It's a pretty hard one.
Would you expect us, like on the test, to be able to know that the aluminum trichloride and how that reacts, or are we more just, as long as we know that the chromic acid is going to take that intermediate?
Depends on the question asked. If I ask you,
Because he hasn't run the test yet. That's what he-
well, no,
He
it's
doesn't know.
literally the question that's asked. I give you these two species, and I ask, what's your electrophile?
The R.
Your answer is that R group. Okay? If I ask, how do you go from benzene to the, what do we say, para-nitrobenzoic acid? You don't need to know how this works, you just need to know it works. And that's what it does. So it depends on the question asked. Okay, I can't just say, yes, that's the question, that's always going to be the way it's going to work. There's all sorts of different angles that come to that. I could also ask, how does this reaction work? I give you the reactant and the product. For our aluminum, our alkyl chlorides. Let's box it in for people listening in. We take a look at that reaction itself, and I say, how does that reaction work? Provide the curved arrow mechanism explaining how you get a positive charge on that carbon. Okay, what would you have to do? The exact same thing that we already went through in the slides on Thursday or Tuesday, looking at how the Lewis acid interacts. Aluminum has an empty p orbital. Electrons from the chlorine can share with the aluminum. We form a very unstable intermediate. Why would this intermediate be unstable? The aluminum is negative, which isn't particularly a good thing, but it's not particularly a bad thing. Chlorine has 2 bonds. So what is chlorine going to do? It's going to steal electrons. In the process of stealing electrons, what do we make? Our cation, and we get our aluminum tetrachloride anion. Okay, which was drawn much, much neater on Tuesday. Okay? So depending on the question asked, you can be looking at varying levels of difficulty. Do I just want you to show me an answer? Do I want you to explain how that answer is formed? If I ask you to explain, I'm going to give you beginning and end. Because the explain question is asking for how do you get from the beginning to the end. So you'd have to provide the mechanism.
So this would show 3 possible steps then?
So,
Or is that considered one step?
so this is the next part of this. We need to go back to our problem at hand. Okay? So are we okay, sort of at least figuring out all the reagents that we need here? Okay? Now we have to add the whole extra level of difficulty to figuring out the order in which these 3 steps must occur. Do we? What's your first step?
Chloride, you have to get that thing on there first, and then you do the chromic acid, and then you
So
do
our
the
first step,
nitration.
I absolutely agree. We do need to get the alkyl portion onto the structure. I definitely dispute the second step.
And that directs the NO2.
If we go to the second step first, look at atom X. Atom X is what atom? A carbon. What's the possible resonance structure for that carbon? Positive. If it's partially positive, does it have more electrons or less electrons than a hydrogen atom? Less electrons. If it has less electrons than a hydrogen atom, where does it direct? To the meta positions. We put our nitro in the wrong position. Okay? So that means we can't add chromic acid before we do the nitro, because if we do that, that step doesn't work. We still don't get our product. So how can I get the nitro added to the para position? It must be added in such a way that it is directed towards the para position. What kind of a group, what kind of atom X directs to the para or ortho positions? An activator, one that has more electrons than a hydrogen atom. So we could look for lone pairs. Nothing in here has lone pairs for atom X. But what do we have? Okay, let's go ahead and highlight this in red so it stands out a little bit better. At that position, what's atom X in that case? A carbon atom. Do we have any groups that can draw electron density away from that carbon atom? No. So it's just a carbon atom. I compare a carbon atom to a hydrogen atom. Which one has more electrons? Carbon. This group, or that carbon, activator or deactivator? Activator. Where does it direct? To the para position. So what should I add before I add chromic acid? I should add my nitration reagent. Okay? What happens in that case? If I go after step 2, okay, I still have my benzene ring. We've got the isopropyl attached. Now where does the nitro go? To my para position. I now have the arrangement of my substituents that I want, the para arrangement. but I don't have the benzoic acid. I don't have that carboxylic acid. How can I convert my alkane, my isopropyl, into a carboxylic acid? I can oxidize it with chromic acid. There's step 3.
Do you know that step again with the carbon, how you get?
Okay. I'm much to, I'm sure, everybody's disdain, I'm going to erase everything and restart from the very beginning, even drawing out all the stupid benzene things at the beginning. Okay? So what we're trying to do is convert benzene into a very sloppily drawn. Thank you. That makes me feel better. Okay, our para-nitrobenzoic acid. Okay, what was our first step? What did we say we had to do first? Okay, we had to add our R+. How did we add the R+? Our isopropyl chloride. Sorry, let me make that look a little bit cleaner. And aluminum trichloride to do. Where on the ring should that isopropyl group go? Doesn't matter. Why? All the hydrogens are the same. We're doing a substitution reaction. None of those hydrogens are different. We're fine to put it wherever we want. Next step of this reaction. We have to add our nitro group. How do we add the nitro group? Reagent. Where does the nitro go? To the para position, because atom X in this case is a carbon. Activating group. There's our NO2. And our very last step, we need to add chromic acid. What does that end up doing? That oxidizes our isopropyl group into the carboxylic acid.
So this question basically includes several chapters because you're oxidizing that area.
Kind of, sort of, except all this material was in chapter 9. But yeah.
It's very nice how you review that.
Positive reinforcement. Okay. How else could we specify all this? Because ultimately, the question that I asked was the reagents. What chemicals did you need to do this in? And the order. So the other way that we could have phrased this would have been to write step 1, our isopropyl chloride with aluminum trichloride, followed by step 2, which was HNO3 and H2SO4. Sorry for those of you saying H2SO4 first. And step 3, our chromic acid. Okay? Questions about that one? Okay? Long, tedious, it builds on itself. You have to be constantly referring back to the material, making sure that you're not making a mistake as you go through. Okay? Some of this does show up in other chapters, like the chromic acid. Okay? That's an oxidizing agent, which we've seen before. HNO3 and H2SO4. How does that make our electrophile? What type of chemistry happened in here to make our NO2+, our nitronium ion? Acid-base chemistry. Okay? So our acid-base chemistry that we looked at so long ago is showing up. We've got our redox chemistry up here. What's happening in our first step? Ultimately, it's a substitution reaction. A little bit more complicated with the EAS, But what functional group is this? It's an alkyl for the carbons and halide. It's an alkyl halide reaction. Okay? So we're pulling from information from the entire sequence of materials so far. Okay, yes, all of this shows up in chapter 9, but you're right. We have to pull our knowledge from everything that we've seen so far. Okay? To form the R group, see if you guys can get this one. This is a little bit trickier. Our isopropyl cation. How did we form that? What type of chemistry occurred there? Lewis acid, Lewis base. That was Lewis acid, Lewis base chemistry. Okay? It may seem a bit daunting, but remember, you got that 8.5 by 11 sheet of paper. Make sure all of those reactions are written down. I'm still in the process of trying to compile all the reactions and post those so you can see those all in one quick, pseudo-quick, easy reference. Okay? I'm getting closer. I'm just not there yet.
Or is that gonna be something we get before exam, or something that's included?
I haven't decided. With structures, it will be before the exam. Just as a list of reagents, that I might staple to the exam. I won't say what it reacts with or what it produces, but I might list the reagents. Okay? Questions about that one? Okay, so let's erase. Let's just go ahead and move forward. We'll come back and do some more of those if we need to. Do you guys feel you need to? Okay, we'll take that as a no. So, chapter 13, with our carbonyls, very few things that I'm going to test on for the exam. Primarily, for the exam, what you need to be responsible for. I promise, 100% guaranteed nomenclature. Okay, you will probably have, just like with every other exam, 3 nomenclature questions. One of them will be naming an aldehyde. What functional group, what class of functional group is in an aldehyde? As a hint, it's chapter 13. It's a carbonyl. And I will also ask a ketone. What class of functional group is in a ketone? Also a carbonyl. Okay, so you need to be able to name those, mainly because I don't want to have to talk about it after Thanksgiving. Okay, you'll notice there is a synthesis question, question 13. You've done all of that chemistry already. In the process of forming carbonyls, where do those carbonyls typically come from? What does a carbonyl look like? Let's try that. Where might be a good place to get a carbon-oxygen double bond from? Do you think it all happens at once? We take a carbon and oxygen, boom, double bond. Probably going to happen stepwise. You're right. Chromic acid reacting with what, though? No. No. On a benzene ring, sure. Alcohols. Secondary alcohols with chromic acid give you ketones. Primary alcohols with chromic acid give you carboxylic acids. Okay? What if we used PCC, politically correct chromic acid, and it stops it at the aldehyde or ketone? Okay? So we have seen those syntheses before. It's pretty much just going to be a review of those kind of questions. Okay? That's what that homework question is on. As far as naming, you've seen this slide before. I've kind of tried to go through and include things as we've gone through it. Halides we've always put at the lowest. We've got our ethers, which we barely looked at. Our alkanes, alkynes, alkenes, the amines, the alcohols. We've looked at all of those so far. And I've tweaked the naming a little bit because it's necessary, because we've now added enough higher order functional groups that some of them take dominance over others. For instance, if I had an alcohol and an amine in the same structure. Alcohols are higher priority. My ending would probably end with all. But then how do I name the amine? We can refer to it as an amino. Okay? So we'd refer to where the amine is based on an amino hydroxy or alkanol, something. Okay? And I think I've got an example with some of the others. If we move up to ketones and aldehydes, our primary nomenclature system for ketones, we change the ending to our own ending. Okay? That's at least kind of helpful, just like with the alcohols, because we get the ONE ending already in the name. When it comes to aldehydes, change the ending to AL. Okay? You might see some referred to, some simple aldehydes referred to strictly as aldehydes. Yeah. Okay? So I should have been talking about this last week, see? Okay? So those are going to be our primary endings. If for some reason we have aldehydes and ketones, what we'll refer to is we'll pick the one that's highest priority, and we'll refer to the other one based on oxo. Okay, again, we'll talk about that in a second case here. Okay, those would be the higher order nomenclature. I will test on our lower order nomenclature. Okay, so when we go through with our primary rules, we'll find the longest chain that contains the carbonyl when it comes to aldehydes. We'll go through and assign our suffix, our meth, eth, prop, butes, all that fun stuff. We'll ignore our halogens, ethers, all that kind of fun deal. Start your numbering at the carbonyl. That will be carbon number what for an aldehyde? An aldehyde looks like what? That's probably a good thing to draw on here. Sorry. We've got a carbon, oxygen, there's our carbonyl. An aldehyde, one of those carbon bonds that's left over is a hydrogen. So we'll start our numbering at the carbonyl, which means every single aldehyde has the carbonyl at position 1. That's where our carbon chain starts. Okay? We'll change the ending to that Al, so we'll get, if we had a 4-carbon chain with a carbonyl, butanal, 4 carbons for bute, the Al ending for the aldehyde. Okay? We don't need to specify the number, okay, of where the aldehyde is. Why? It's the end of the chain, the beginning of our chain, for that matter. So it's always going to be position 1. We don't have to add that extra information. Okay? We can then go through as we have with everything else. We'll name our substituents, assign the numbers for every single substituent. So even if you have multiple substituents that are the same on the same carbon, you have to specify every single number. Okay? Assemble your whole name together in alphabetical order, and you should have your final. I did actually want to go to the next slide, but that was an accident. And you'll have your final name for your aldehyde. If we move to a ketone, what are we looking for a ketone? Sorry. We still have that double bond carbon-oxygen, and now we're looking at coming out to carbons. Okay. Just because I drew this terribly, I'm going to ask it. What's the bond angle there? 120. What's the bond angle down here? 120. Ideally, you should draw it so you reflect those bond angles as best as you can. Okay. Clearly, I'm not doing it, so I'm not going to expect you to be that accurate with it either. Okay. Very similar rules when we go through and naming it. Okay, we'll find the longest carbon chain that contains the ketone. We'll assign numbers to the longest chain, and we're going to assign it in such a way that we give the lowest numbers possible to our carbonyl, where that ketone is located. That number will change. Why will it change? Unlike the aldehyde. It's got to be a secondary carbon, which means I could have 1,000,000 carbons out that way and only 1 on the left side. Or I could have 2 carbons out there. The number's almost always going to change depending on the name. Make sure you number it, giving it the lowest possible number. Okay? So you will have to specify that number when you go through with your numbering. Okay? When you go through with your name. Okay? Then go through, name all your substituents, and assemble everything together. Okay? If we assume the structure that I've got drawn here is just filled out with hydrogens on the rest of those carbons, how do we go through and name this? To start off with, what do we got to do? Number one rule. Longest carbon chain. There's our longest carbon chain. How many carbons are in that longest carbon chain? We've got 6. So it's going to be, what's our suffix? Hex. Okay. All of our carbons except for our ketone are singly bonded. So we can specify that by making this hexane without the E ending. Okay, we haven't finished our name yet, just hexane. Okay. If it was just carbons and hydrogens, then we could finish off with hexane. But we have a carbonyl in there. So what's our ending going to become? Hexanone. Come on, right? There it is. Okay. Where is our ketone? Or our carbonyl? At position 3, we get 3-hexanone. There's our name. Questions about that? Okay. So, some examples. This is going to be embarrassing. I haven't worked any of these. Let's try and put these structures together. We get 3-methyl-cyclohexanone. Where should we start? Okay, we could go through and do it that way, but you know me, I'm going to be more difficult. Go easier. I see an ONE ending. I see an AN ending. I see a hex. I see a cyclohex. Okay, I've now covered the bulk group. Now I'll go through and try and put that together. Cyclohex means 6 carbons in a ring. The AN means they're all single bonds. The ONE ending, it's a ketone. So we can put in the carbonyl. Really? It gets numbered like that?
How would you distinguish between the 2 on either side when it's 1 or 3 methyl?
Yeah, I wonder where I got this name from. Like I said, it'll be embarrassing because I haven't looked at the name yet. So we'll continue to process this out as best as we can. Okay? So that 2 would suggest we're at position 2, which seems really, really weird. Okay? But let's kind of ignore that for the moment. What else do we have here? We've got the methyl. Methyl means CH3. If we decide that our carbonyl is at position 2, where's position 3? Either direction, immediately next to it, there's our CH3. Okay? Does this name make sense? We should be looking at numbering this structure out. Maybe this was one of those nonsensical things that we ask. Numbering it around, so I would end up calling that 1-cyclohexanone, where the methyl's at 2, so 2-methyl, 1-cyclohexanone.
For that one, would you need to write 1 because it's implied?
So the 1 is almost always implied if you want to. Okay, I've got no problems with you implying 1s. Okay, questions about that? Anybody looked at the rest of these? Oh, I know what I did. It's my mistake. Here's why it showed up. Let's take a look at the next question. Sorry, you guys were done with that one, right?
Wouldn't the second one be the same?
So let's address the second one a little bit to that same level of difficulty. We've got the ONE ending, then we have EN, which means an alkene. We've got a double bond. We get the hex with the cyclo in front, so cyclohexenone. So our cyclohex means six-membered ring. Our primary substituent is going to be our ONE, our ketone. So let's go ahead and add that on. We then have the EN ending, which means a double bond, a carbon-carbon double bond, an alkene. Where is that double bond? At position 2. Where's position 2 on our ring? So either direction. I'm going to label, was that clockwise? Now you don't back me up, thanks. Thank you. At position 2 is where our double bond is. Do we draw it from 2 to 1 or from 2 to 3? 2 to 3. Otherwise, we would have been referring to our double bond being at position 1. On top of which, is that even physically possible? You'd have too many bonds at position 1 if we put the double bond there. Okay? As far as the rest of the name goes, we have a methyl, which means a CH3 located at position 3. Okay, and that would be our final structure. We made reference to meta. So we're saying ortho, para, meta, right? Those apply to what kind of a structure? Benzene ring. Is this a benzene ring? No. So we will not apply ortho, meta, and para to this structure because it's not benzene. Okay? Make sense? Okay, so let's give you some more complicated ones then. Let's take a look at the next one. That one's nice and painful. We've got...
The one at the bottom was chemical.
Yeah, we'll come back to that too. So we'll jump to, we'll do this one first, then we'll do the last two. Okay? We got the ONE ending, and then I see an EN, but then I get a pH. That doesn't really make any sense. So it's not an EN, it's actually PHEN for a phenyl. Okay? Then I go back, oh, that doesn't make any sense. OZ, it still doesn't make any sense. What's zo? Or nizo? Or enzo? Enzo's kind of cool. Benzo. Okay, give me a break. It's late. So now what we're looking at is a benzene ring connected to a phenyl ring. And how are they connected? Phenyl, so that's one of the common names for the EAS chapter, our aromatic chapter. A phenyl is an aromatic ring as a substituent on something else. This is an example. I won't ask this on your exam. Benzo sounds an awful lot like benzyl, so what we're probably looking at is an extra carbon in between. The ONE ending suggests a carbonyl. There's our benzyl and our phenone, or our phenyl. Okay? And since that's not on your exam, let's just go ahead and erase that. Jump to, we said, the last two possibilities. Since we're going to make it only what you're going to see on your... That's what I was thinking about doing, actually, yeah. 3 won't be. So we can cross 3 off because that's looking at aromatic nomenclature, which I said you don't have to worry about. Which would also mean that next one, the 3-phenyl propanol as well. Because that phenyl is still part of our EAS nomenclature. So this 4-hydroxybutanol, okay, so we can go through and try and piece this name together. Start at the back. AL ending means aldehyde. AN ending just single bonds. The butane means 4 hydroxy, means in OH. Okay? Remember how I said based on priority we may end up shifting in other names for each of those pieces. Okay? And then the 4 would refer to the position of the hydroxy. So if we put it all together, we get 4 carbons. 1, 2, 3, 4. Where's our aldehyde going to be? Position 1. Does it matter which side I picked to put it on? No, I just picked that side because I think I can draw it prettier there. Okay, so there's our aldehyde at position 4. I have a hydroxy. So we could go through and count through. 1, 2, 3, 4. Good call with our aldehyde. Our aldehyde is the highest priority, so we'd have to specify that at position 1. So at position 4, I have a hydroxy. One of the things I want you to watch out for, so do not copy this. This is a bad thing to do. I took away a carbon by doing that. Okay, so I must add that extra bond to show the hydroxy. Okay? Oh, how cute. Any questions about that? Okay. I won't ask the last one on the exam, so do you guys want me to go through it? No, thank you. Okay.
Just draw it, don't like break it down, I just wanna see what it looks like.
I don't understand the carbol.
I'll show you that in a
That's
second.
the only part that- or carbol, yeah.
Cyclohexane, hydroxy. There's our aldehyde, but that's not really part of the bulk chain with our cyclohexane. Okay? So that's why we have to throw in the carb as an extra carbon so that we can get our aldehyde added as a substituent. That's where it's coming from.
Is that what that means? Carb? It just needs extra carbon?
You're adding that extra carbon in this case. I think you only see it with aldehydes. Okay?
Well, we don't have to worry about
So
it.
forget that.
Doesn't matter.
No, don't worry about it.
Gonna draw
I've already
it
forgotten about
a lot easier than
Yeah.
what did it expect?
Okay? Questions about any of that? Okay, so as far as what material you're responsible for the exam, so let's kind of push through some of this stuff. We've got chapters wise. See if I can pull up from my memory. We get chapter 4, which told us what? What information was in chapter 4? Alkene, and in particular, nope. But you're right, alkynes show up in there too. Aldehyde Nomenclature. Okay, and we saw some structural information. What do we mean by structural? What was that?
Cis and trans?
Yeah. Cis trans. Why is pen not writing? Cis trans, also known as REZ. We might also see some questions, and by might you will see some questions on hybridization. Okay, hybridization, bond angles, that kind of fun stuff. Okay, we then moved into chapter 5. What was chapter 5 all about? Now we looked at alkene reactions. I'm just going to write RXNs. Okay, there were a lot of alkene reactions. Okay. And with each of those reactions, it's not just knowing the reagent, because the reagent's important. So you have to know the chemicals used. You then also have to know how it worked, which means mechanisms. Okay. Then you also needed to know, which comes back to mechanisms, stereochemistry if it was important. Okay, how it affected your overall products. Okay, so chapter 5 is probably going to be the most difficult section here, at least in my opinion it is, because of the sheer amount of reactions possible and very quickly, easily variable reactions that we can get out of it, and the different mechanisms that come through. What? Yes?
RS applies.
So RS applies kind of, sort of, when we're looking at our alkene reactions. What mechanisms would we be looking at for alkenes? We get addition reactions. So in the process of doing an addition reaction, we move from sp2 carbons to sp3. When is stereochemistry important? What kind of a carbon? A carbon with 4 different things attached. The hybridization has to be sp3, which means addition reactions can have issues with stereochemistry because you're forming sp3 carbons. Okay? What other types of reactions might involve alkenes? Elimination. Okay? One of the primary things that I'm concerned about that you guys are getting bogged down in is all the reagents and the mechanisms, and you're losing sight of the ultimate goal, which is looking at an individual structure and trying to predict something about its chemistry. Okay? What do I mean by that? Well, if I give you an example alkene, first off, you should be able to show me double bonds. And you should look at that and now say, these are the possible things that that species can act as. What does that structure provide for reactivity? The double bond. And in particular, even better description, the pi bond. What is in the pi bond? What does that equal? Electrons. What kind of a species could donate electrons? Lewis bases. What else? Bronsted bases. What else? Nucleophiles. Okay? So I want you to look at these functional groups and trigger on this type of chemistry. What thing is in there? What thing is reactive? How can that species move on to something else? Okay? And if you have an understanding of this material, particularly if you're given a list of all the reagents that you can react it with, you now know that it doesn't make sense to react it with a base. Why not? Because it is a base. So what happens when I take a source of electrons like a pi bond and I bring it near another source of electrons like a base? They repel away and I don't get a reaction. Okay? So being familiar with some of that reactivity can help you predict your reactions or what reagents you should be using. Okay? Along with chapter 5, I'd kind of group chapter 8 in with that. So before I move to a new slide, we've got our chapter 8, which was technically our alcohol chapter. Man. Just like my wife says, like a 5-year-old. Can't even draw. Is that right?
Yeah, sure.
Now it looks like a D.
That's great.
Just do AL.
How?
Okay? That was technically your alcohol chapter, but a lot of the reactions in the alcohol chapter resulted in elimination or redox, which brought us into aldehydes and ketones, okay? Which we aren't too concerned about reacting those, but we are concerned about making those from our alcohol chapter. Okay? We also saw the formation of epoxides. Okay? So epoxide formation and reactivity. Okay? Why would we come back to epoxides? Well, to make an epoxide, what did I start with? What was the reagent? You guys remember that from one of the quizzes?
MCPBA.
PBA added to
Double bonds on either side.
an alkene. Okay? So some of the alkene material shows up in that chapter as well. Okay? You're not going to like it, but I'll try it. I'm going to have to clear everything first. Everybody got that copied down? Okay, maybe I'll try and just squeeze it in. Like I said, you weren't going to like it anyway. We react the alkene with MC, come on, CPBA. The result of that, carbon, carbon, there's an epoxide. Okay. Why are those even further obnoxious? How do the epoxides then react in most conditions? We can add a nucleophile, and we do a pseudo-internal substitution reaction. Okay? Our leaving group is actually attached to our substrate, and it stays attached. Okay? So we could have a nucleophile come in and react, okay, kicking out our leaving group. Okay. Other things that came out of those chapters was looking at your alkyne reactivity. I think that's a little bit too busy, so let me draw the alkynes on the next page. Everybody's okay with everything up there? Erase it goes. With our alkynes.
Which chapter is alkane?
Alkynes are kind of interspersed in between with the alkenes. As far as you guys are concerned, they react virtually the same because of the pi bonds, except for this one new reaction. Or not new, because we've talked about it. The alkyne is what functional group? A triple bond between two carbons. If we have a terminal alkyne, we call it a terminal because it's the end of the chain. We've got a hydrogen out there. This introduces some new chemistry to us. It's not just the pi bond. What's the hybridization of that carbon atom? It's sp. What happens as we decrease hybridization, as we go from sp3 to sp? Lower in energy, what happens to where the electrons are held? They're held tighter, which means we are effectively increasing the electronegativity of the carbon atom by decreasing the hybridization. What does that mean to us? What then happens to that carbon-hydrogen bond? Weaker or stronger? It gets a little bit weaker, weak enough that that can act as an acid and we can react it with a really strong base. Okay? As far as I'm concerned, I'm not going to put the sodium on it because everybody's getting bogged down in the sodium ion. So you'll see it as amide NH2-. You might even see the extra lone pairs. That can come in, react with our hydrogen. Hydrogen now has too many bonds, so we can take these electrons and push them onto the carbon. What does that produce? A negatively charged carbon. What's special about a negatively charged carbon? It's a great source of electrons, also known as nucleophile, also known as Lewis base. You can answer them all faster than I can answer them. Or that's where I was going. B base. A Bronsted-Lowry base. Okay. I was feeling I was going to mix base with Bronsted and it wasn't going to come out nicely. Okay. So the alkynes also showed up. That's going to be our primary reaction. That interaction right there, making the negatively charged carbon, is really important because we now have a really good nucleophile. Okay? Which, believe it or not, your carbon-carbon bonds are really difficult and fairly rare to make. Why? What can you tell me about the polarity of a carbon-carbon bond? It's nonpolar. Okay? Which means there's very little reactivity. If there's very little reactivity in the bond, what does that mean about the reagents? they have to be really, really reactive, okay? Which means they're fairly rare. We don't very often see fully charged carbons, either positive or negative. The positive ones are a little bit more common, but the negative ones are very, very, very rare, okay? So what's nice about this reagent is we can form carbon-carbon bonds because we now have that negative charged carbon that can react with some of our carbocations. Okay, so it's pretty important. Okay? Which is a lot of what that failed quiz 8 was attempting to get you to work with, was those alkynes. Okay? Everybody good with what's written on there? Okay. Last thing that we'd be looking at would be Chapter 9. What's in Chapter 9? Coarse mechanisms, but we can get a little bit better about that. We get Chapter 9, which was all about our arenes, which as far as you guys are concerned equals benzene to a certain extent as far as the reactivity goes. The very first thing we learned within that chapter, aromaticity. Okay, so those are Huckel's rules. We went through those 4 rules, how many electrons, sp2, hybrid orbitals, all that fun stuff. Okay, so you need to be able to apply those rules given a structure. You should be able to tell me if it's aromatic or if it's not aromatic. Okay. After that, we went pretty much into the benzene reactivity, okay, which came into 2 classes. We had the electrophiles, okay, and I kept listing them out today, or mentioning them, the 6 electrophiles. So if you go back to the slides where we look at speeding the reaction by adding a catalyst, those are those 6 electrophiles. You need to know what those electrophiles are, where they're coming from, how they work. Okay. Then we also had the nucleophile. What was the nucleophile in our EAS reaction? That was our aromatic ring, or like I said already, benzene. It's what we're going to drive at. I don't want you to get any more bogged down in the chemistry. Okay. So we can do our electrophiles with increasing their reactivity. With our nucleophiles, we couldn't add an extra thing, so we ended up shifting, making it more reactive by changing the substituents. So we get substituent effects. And that's where we got our activators, which are your para-ortho-directors, your deactivators, which are your meta-directors, okay, and then your halogens, which just mess with you. Okay. As far as other things that you're responsible for there, you of course have your mechanisms showing up again. Okay. Are we concerned about stereochemistry? Should we be concerned about stereochemistry with EAS reactions? No, why not? What's the hybridization of every atom on the carbon or benzene? sp2. Needs to be sp3 to be concerned about stereochemistry. So what we'd be concerned about, I won't phrase it this way on the exam, but what's referred to as regiochemistry, where your substituents are being added, so your substituent effects. Okay, so we substitute, instead of having stereochemistry to be concerned about, we're concerned about our stereo or our substituent effects. Okay, as far as your mechanism goes for your benzene, your primary one is your EAS mechanism. Okay. Oh. Lists of mechanisms that you're ultimately responsible for this exam. So we can kind of just put those all out here. We've got your EAS. You've got substitution. EAS is a substitution. How many types of substitution reactions are there if we don't count EAS? 2, we get the SN1 and the SN2. You get elimination. You've got addition. And, redox. No, actually no. No mechanisms on redox. I don't expect you to know the mechanisms for redox. What's the last one? Your acid-base mechanisms. Okay? Questions about any of that? Nothing, right?
Super easy.
Okay.
Are we still going to have the unsaturated?
Saturated versus unsaturated is looking back at